Okay, we'll be starting on the chapter of forces, and later on we'll actually cover your pressure as well. So basically, first things first, we need to know what is a force. A force is actually defined as the force is just a push or a pull itself, and typically for force, we usually represent it with a letter with F, and you will have a number, and the units will actually be capital N, N for newtons over here. It's actually named after Mr. Isaac Newton. Okay, so typically when we push or pull any single object, we will basically it will exert a force on it, and therefore you actually produce some form of change. And this is what we're actually interested in. This is your different effects of a force. Now, before we talk more about the effects, let's take a look at your instruments so that we can measure your force itself. Typically, we'll use this, and all three of these, they're actually referring to the same thing. They are actually based off your spring balance, which is basically a thinner version of this. Okay, it will actually have a spring inside, and this spring will be connected to a hook. So basically, if you have any object, you actually tie it to this, and when it actually weighs down, you can actually measure the force. Okay, so this is what we call a spring balance. It's also called sometimes called a force meter or a Newton meter itself. Okay, now when we have an effect of a force, right? Whenever we have a force, whether you are pushing something, pulling something, and all that. Now, let's imagine I have this box. Now, basically, there is no force on this box, but if I push the box will actually start moving. And if I do the opposite, if this box was originally moving like this, okay, what happens if I do the opposite? If I exert a force in the opposite direction, I can actually cause it to stop. Okay, so apart from basically this starting and stopping, they're actually the same as changing the speed, because you're actually just changing it from 0 to something or from something to 0. So these two, they actually can be considered the same. So what I'll say is you should memorize changing the speed, because starting and stopping, they're also considered to be changing the speed itself. And if your object, okay, this is a top-down view, is moving like this, if you nudged it to the side, you actually move it in this direction instead. Okay, so this is why you can change the direction as well. And if you change the shape, this one, this is actually linked to your pressure itself. Okay, so later, at the later half of the video, or basically the next video, we will actually cover more about pressure itself. So typically when we talk about forces, when we are actually doing your worksheets, we're actually more interested in changing the speed. Do you speed up? Do you slow down? Or whatsoever? Okay. So next, let's talk about balanced and unbalanced forces itself. Now, what are balanced forces? Balanced forces are balanced, or forces are balanced when they actually cancel each other out. So what I mean by that is up and down are the same. So what happens when you have any downward force and your upward force? Let's say this is 10, this is also 10. So what happens? They will actually cancel out. You end up with no force acting on it. Okay, 0 newtons, no force. So same thing, your left and right can also be the same. So you can have a separate diagram where this is, let's say, 20 newtons, and this one is also 20 newtons. So because of this, you also have 0 newtons. And the thing is, they don't actually need to be the separate diagram. They can actually be all be on the same diagram itself. So for example, if this is 20 newtons and this is also 20 newtons, basically they are going to be the same diagram itself. We separate them. Vertical forces only, vertical only, or we will look at horizontal only. We rarely actually combine both of them together. So usually, if we do combine them together, usually it will be a much more difficult question, and the question will probably give you more details on this. So how would we phrase it? The keyword is that when forces are balanced, we'll need to use this phrase over here. Very important phrase is no resultant force. Very important. Put a star next to this. So because there is no resultant force, which means I do not, no change in speed. So if there is no change in speed, you will either remain stationary or you will have constant speed. Because you're not speeding up, you're not slowing down, so you're still moving at that same speed itself. So you can see over here, you either move at constant speed or you will still remain stationary. Okay, so a few things you need to take note of, but don't worry about this. Typically, if your school doesn't cover Newton's laws, this part will actually be more of a touch and go. So for those who are more interested, you can read ahead. Okay, so constant speed remains stationary. Okay, so you can see over here, diagram-wise, your rightward force and your leftward force are the same. So what we can write here is that there is no resultant force. Okay, and since there is no resultant force, my object is either, number one, you're either stationary, or number two, you're moving at constant speed. Okay, now, on the other hand, if your thrust is greater than your air resistance, so what happens? You will have a resultant force. Okay, you will have a positive resultant force, or you have a positive resultant force, and that's why you see in this part you will actually speed up. So when you speed up, basically you will affect other things, and then therefore this whole explanation is so long. But basically, if you're just gonna ask yourself, am I gonna speed up, am I gonna slow down, or am I still moving at constant speed or stationary, you just need the first line all the way to the speed up. For the rest, that one is actually more for upper sec stuff. So just read ahead, it's mostly FYI for now. Okay, now unbalanced forces is actually basically this part over here. Okay, so your unbalanced forces is when you do not cancel them out. So what happens is that you can see over here, you have 8 newtons and you have 5 newtons, right? What happens is that you will, so this word here, accelerate, means speed up. Okay, so you can see over here, if you take your 8 and your 5, you end up with 8 minus 5, you have a 3 newtons. So your resultant force will be 3 newtons, and this will be to the right. Okay, so what happens is that this object will actually speed up to the right. Okay, so you can write down here. They're not letting me write this. So your object speeds up to the right. Okay, so if you have two forces in the same direction, what happens is that they actually cause it to speed up a lot more to the right. Okay, so you move to the right faster, you speed up faster if you are comparing between the first and the second one. And if you have two forces, one vertical, one horizontal, they do not cancel each other out. So what happens is that you will learn this in set 3, is that you actually have a new resultant force, which is mostly diagonal. Okay? So don't worry, don't be too bothered by this for now. The first two is the one that you should be more familiar with. Now, let's try some example itself. Basically, your resultant or your net force is actually the sum or the difference between your forces. So when do we use sum? When they are actually the same direction, 7 newtons, and this is to the right. Okay, when they are same thing, 5 and 7, they are in the same direction, is 12 newtons, both is same thing to the right. And if you see that they are actually in opposite directions, we actually minus them away. So we take the bigger one minus the smaller one, 7 newtons, this will be to your left. Okay. Now, similarly, if you do the one below, this is 9 newtons to the right. This will be 0 newtons. There is no direction. And basically, this one will be 9 newtons, and this will be to your left. Okay. And just be careful. Some schools, they don't actually accept resultant force is 0. If you're explaining it, you should write that there is no resultant force. Okay, so there's no direction over here. All right. So let's take a look at the next page. Basically, this page, if you have the book with you, might be slightly different. So that's why I actually colored the differences over here. So for non-contact forces, they are all push and pushes. So first thing, before I go into the detail, now a force itself is very, very vague, right? It's either push or pull. So we actually try to separate them into two different types, which is one is a contact force and one is a non-contact force. Okay, So a non-contact force is a force or a push or pull that can act even if your objects are not touching each other. So what are the examples of your non-contact forces? They are your gravitational force, your gravity that's pulling you down, your electrostatic force that has to do with electricity, and your magnetic force that has to do with magnets. So if you notice the amount of detail given is that the electrostatic force and magnetic force, they are quite rare. We don't actually touch on them a lot. Most of them are actually very straightforward answers. If you have a magnet, if you move them closer to each other, you will repel and attract. Same thing for your electrostatic as well. So the most important one, or the one that the schools usually focus on, will be your gravitational force. And this gravitational force is what we also know as weight. Okay, so for some of you who have already done your mass weight density chapter with me, this is actually a recap. Your weight is actually your m times g. Okay, so I'll write it at the side to highlight it. Weight is your mass times your gravitational field strength. And typically on Earth, your gravitational field strength, which is this part over here, is actually 10 newtons per kg. It's usually a fixed number. So usually the question will either give it to you, or if they never say it, it will just be m times 10. Okay? However, if you're on a different planet or on the moon or whatsoever, basically your G might actually change. So it's not always going to be 10, but as long as you're on Earth, it will always be 10. Okay? Now, basically, apart from these three forces, every other forces are what we call contact forces. And what exactly are contact forces? Contact forces are all your push and pulls when they are touching each other. So as the word contact means, it means that you must touch. For non-contact, you don't have to touch, or you can touch. So this is more of an either or scenario for your non-contact force. Because if you think about it, right? When you're standing on the ground, you have your weight pulling it down. If you are in the air, you also have weight pulling you down. So the weight doesn't actually matter if it's touching you or not touching you itself. It will just pull you downwards, because even though you're not touching the earth will actually still pull you down based off gravity. Okay? So all your different types of forces itself, you have all the different types listed in this table. This weight is your gravitational force. Okay, so for those who you haven't kind of linked an idea that the weight is a force, is that this is gravitational force. So you can usually denote it with either you write weight or you can write your gravitational force GF. So your will always be vertically downwards because Earth is beneath our feet. And for normal contact force, we usually denote it with NCF or sometimes just N by itself. And it's a bit special. Normal contact force will always be perpendicular to your surface. And this is to every surface. Okay, so if you are sitting on a slope, for example, your normal contact force will be 90 degrees over here, normal contact force. Okay, for tension, we usually call it T. Compression, we also use it T. They're actually kind of the same thing. Okay, so when you have any kind of string, spring, or rope, basically it's always towards the string, or rope. So for example, if you are pulling a box, first thing, your object will be the box. So you will start from the box towards the rope. So this is your tension. Okay, so this is the tension on the box. Then for your frictional force and your air resistance itself, frictional force, we denote it with a small letter F. And for your air resistance, we denote it with a very big R for resistance. Okay? And for your applied force and all that, all of this, including your lift, they are also considered to just be F. Okay, so F will just be for the rest of it, which is not weight, normal contact force, tension, frictional force, air resistance. The rest will just be labeled as F. Okay, so do take note, this one can be from engines of cars, vehicles, etc. Okay, also can. So just take a look at this. So the thing is, from this diagram, we'll use it to actually help us solve your force diagram, or what we actually call your free body diagrams itself. Okay, so do take note, sometimes you will see me refer to this as a free body diagram. Okay, so first thing, a free body diagram itself is basically all the forces acting on one single object. So before you do anything, we always try to identify what is the object. The object will just be your painting in this case. So your painting itself is the middle one. So every object has mass, which means every object has weight on Earth. Okay, so because you have weight on Earth, there will always be a vertically downwards weight. And if this is a question or ask you to sketch and label, we try to write it out in words, and then we label the symbol W. Next, because this painting is actually just hanging from the pin, basically there is no contact surface area with the ground or anything like that. It is above the ground. So what happens is, if you notice that there is this string itself, each string will have a tension. So I will write this tension T and tension T. If you want to label, you can label them T1 and T2, that's fine. Okay. Basically, you will have two tensions because your object that you want to focus on is this entire painting. So we are not including the string, and we are not including the pin itself. Okay, this is the pulling force by the string, pulling force by the string, pulling force by the earth. So to take note, you should have three forces for the first one. For the second one, you are being pushed by an external force. Usually this is just your applied force. Okay, and this is across a rough surface, so you will have friction. So first thing, every object has weight. And since it's touching the ground, there will also be a normal contact force. Okay, so write this properly in full. Normal contact force, NCF. This is your weight, W. And because there is a pushing force, it should be towards the box. This will be your applied force. And because we have a rough surface, we will also have a frictional force. Okay, a bit small to write, but basically you can see this. Now, if you were sketching on your own, you can use the symbol straight away. But if this was an actual question itself, you will need to actually label everything nicely. And next, same thing, you will always have weight. And because you're resting on the surface, you also have a normal contact force. And your normal contact force itself, now, because without anything, your box will actually slide down. So you will also have a frictional force as well. You only have three forces. Because keywords, you are at rest. When you're at rest, means you're stationary, your resultant force. There is no resultant force. Okay? Which means you should have everything cancelling each other out. Okay? All force cancel out. And you do have a rough surface, so I must have some form of friction. Okay, so because of that, your three forces, even though some of them are diagonal to one another, they will actually cancel each other out very nicely. Okay, so next, you can actually try to do the checkpoint itself, but basically, let's talk about this question. First thing, you are at rest. You are motionless. Oh, hang on. You are motionless. You are sliding across a smooth table. When you see the word smooth, it means no frictional force. Okay, so you are sliding across it. Next one, let's talk about this. Okay, let's do the first three first. First thing, you are, when we draw a free body diagram or your force diagram itself, usually we only draw the object that we are focusing on. So typically, we'll draw our favorite box. So every object will have weight, and because it's resting on the table itself, you will have normal contact force. And since my object is hanging from a rope, first thing, every object has weight. And because you're hanging from a rope, most likely you should have a upward force. So because you will have a tension. Okay? Because your rope is connected to the top of my box, and therefore it will not move. Because if you actually put it in left, right, left, right, or down, you actually cause it to speed up in certain directions. Because remember, when you have no resultant force, that's when you are stationary. So if you know that you are stationary, you can actually work backwards. I must have no resultant force. Same thing, no resultant force. Smooth table means no friction. So if you draw your box, every object will have weight. Because you are sitting on the surface, you have normal contact force. And when you're sliding across a table, first thing, nothing is pushing the object and nothing is stopping the object. So there is actually no horizontal force, even though it is moving horizontally, which is kind of weird, but this is just how it works. Okay, because of the fact that there is no friction. Next, let's talk about this one. When you have a smooth floor and you're being pulled by a rope, you have rough floor at constant speed, rough floor with increasing speed. Okay? And being pushed, pulled. Slightly different. So the thing is, when you're being pulled by a rope, first thing, our favorite box, your weight, your normal contact force, and you're being pulled by a rope. So this is tension. Next, constant speed. Resultant force is 0. You have a rough floor, you will have F. So, favorite, weight, normal contact force, you are being pulled, tension, and you actually have a frictional force. Okay? Next, you have increasing speed, means my resultant force will be positive. Okay? Or positive. Which means that my rightward pulling force, pushing force, is actually stronger than my frictional force. So this F is much bigger than my small f. So you can see, you can draw it by drawing the arrows longer. So if my pushing force is longer than my frictional force, it will cause it to speed up. Okay. And next, if you toss the object up before you leave your hand, first things first, before you leave your hand, which means still in your hand is touching your hand. So you can either say that this is a normal contact force, or you can just say that this is an applied force. Basically, it's the same thing. Now, when you're at the highest point of your object, it actually stops moving. Okay? Some of you can just play with your stationery, just toss it lightly in the air. You'll notice that you will actually stop at a very short moment of time, that it actually stops moving. And because you stop moving itself, oh, sorry, I forgot, there is also going to be air resistance. Okay, so because you stop moving itself, you only have weight. Because when you don't move, you don't have a frictional force. And because you don't have frictional force and you're not touching any other thing, you only have one force, which is weight. But as you keep falling, what happens is, as you fall down, your air resistance will try to stop you. So because of that, you have two forces over here. Okay, so I will actually stop here for the first part.